the webinar. I forgot to do that at the beginning. I apologize. But if you were to kind of implement one improvement to the earthquake early warning system in Japan, what would it be?
You mean the process for the improvement?
Yeah, or any kind of improvement. Like what is kind of the next limitation of earthquake early warning in Japan needs to be addressed?
Limitation.
Yeah.
One of the limitations is of course, the observations is a network. But some of the network is not actual. We have a good network, but many of them are the trigger type, not real time, not real time data transmissions. So all station is data sending is a real time, so we can more dense observation network for the earthquake early warning. So I think one of the observation networks is one of the important factor to make a real time data transmission. That is one of the important factor for more enhancement of earthquake early warning.
Okay, great. Thanks again, Dr. Hashiba. That was very interesting. So next.
Yes, thank you very much. Oh, thank you very much.
You're very welcome.
I'll stop that sharing. Okay.
Yeah, perfect. Thank you. So next we have Associate Professor Susumu Ono from Tohoku University. So Professor Ono is a professor at the International Research Institute of Natural Science at Tohoku University. And he will talk about structural health monitoring with earthquake early warning. So thank you, Professor Ono. The stage is yours.
Thank you for introducing me. Can you hear me?
Yeah.
Okay, thank you. So my title is Structural Health Monitoring with Earthquake Early Warning, and I'm belonging to a earthquake engineering laboratory in Tohoku University. So this is introduction of my presentation. So as Hoshiba-san said, earthquake early warning is a system to alert arrival time and the intensity before arriving the main shock motion. And this is useful to move to a safe place and facilitate shutdown like elevator stop. And sorry. And the structural health monitoring system has been widely used in earthquake engineering community. So this system is to use check structural safety to sorry, to use a check safety after earthquake by using a monitoring sensor from sensors, usually accelerometers. This is used for rapid damage estimation and to use judge if people can stay in the building after the earthquake. So in this presentation, I will introduce our EWSS system, which is investigated in the Miyagi area, introduced. And I will show you advantage of using SHM system with EEW. So this is system characteristics of our system. So there are two functions in the SH system and EEW system. As a SHM system, at least three sensors are installed in the buildings, mainly in the municipal office buildings. And these sensors can measure from very weak to strong motions and continuous recording and transmissions. So this enables the conducting a continuous and real-time seismic haze monitoring even at distant buildings. And these records are transmitted to IRIDES buildings continuously. And as a EW system, this system has operated by a short packet transmission in order to use a real-time waveform, and VPN using DSL and optical fiber. So by using this system, we can predict a strong motion at target site from front side data. So this is a history of our system. Before 2011 Tohoku earthquake. This network is originally planned and installed by Professor Motsuka in Tohoku University for research and development purpose. And at first, CEA, civilian earthquake engineering building in Tohoku University in Sendai. Sendai is here. This is a Miyagi Prefecture, and this is Oshika municipal office buildings at the edge of Oshika Peninsula. Nearest point to the epicenter occurred in the offshore earthquake, and we added the other sensors, but in 2011 Tohoku earthquake, Ongatsu building suffered severe damage by tsunami and demolished, and CEA buildings were also severely damaged and demolished. So, and the current network configuration is here. So the red colored squares is some schools or municipal buildings in city office buildings in Miyagi Prefecture. Miyagi Prefecture is here, and we are expanding the next prefecture like Iwate Prefecture and Yamagata Prefecture. And sorry, this is still research and development purpose, not actual EW system. So in this slide, in this presentation, I will introduce spectral forecasting from front site Oshika to target site Sendai to IRIDES building here in Tohoku University campus. So this is Oshika Municipal Office buildings. This is located at the hard rock site and 3-story RC buildings. And this was completed in 1975. And this means that this building was built according to old seismic standard. So seismic retrofit is necessary. So sensors are installed in each floor, and KNet site is installed in the same site. So this is deformation of the upper structure during the Tohoku earthquake. So the maximum deformation is about 10 centimeters. So this is so the diffraction angle is just exceed 1%. So this is a relatively a big deformation, and this is a national frequency change by system identification method, and so you can see the natural frequency suddenly drops at the strong shaking, the first strong shaking, and the secondary drops to the secondary wave. And so after, so there are some damages, and so seismic retrofit works were conducted after this earthquake. So, and this is a front site. And this is a target site to predict spectral forecasting. This is these buildings and plan and section. And this building is built on the stiff soil spread foundation and 5-story RC building, but with base isolated devices. So continuous observation system were installed since and operated since the December in 2014. So this is a target site. So we investigate the spectral forecasting at target site from front side data. Front side is Oshika and target site is Ildes. So why spectral focusing? This is just to predict a structural response. Waveform spectral information is desirable, not intensity. So this is a method of spectral focusing. This is a very simple equation. The S-wave power spectrum at target site at Ildes is multiplication of P-wave power spectrum at front site at Oshika. This can be obtained at real time. And we multiply the these two spectral ratio. This can be estimated by previous, before the earthquake, empirically estimated. So after the completion of Ildes, this is data in the epicenter is located in this area. This is a Miyagi prefecture and this is a Fukushima prefecture. And this is epicenter. And from over magnitude is over larger than 5.5. So by using this data, we estimate this from site P to target site S spectral ratio. So this is estimation results, calculation results for this is for Miyagi of Ofu Miyagi prefecture area. This is for Ofu prefecture, Fukushima prefecture area. So you can see the blue one is for estimation for each earthquake, and red one is average for each area. And you can see the spectral characteristics is similar, but the amplitude is there is a variation in the amplitude. So, but so this is a result for each epicentral area in the Miyagi prefecture. So you can see the there are stable results if the epicentral region can be specified. So this spectral ratio can be used for calculating transfer function between the P wave at Oshika and S wave at Ildes. So So currently, the GMA provides us a reliable estimation in the epicenter location. So we can use this spectral ratio to predict power spectrum in the target site. And this is just to predict illness basement. And to predict flow response at the upper structures, we have to estimate amplification in the target buildings. So this is this building, and this is a sensor location. And so basement at the first floor and the top floor. And there are some base isolation devices between the first floor and the basement floor. So base isolation system is a highly nonlinear system. So this is an estimation from SSM system data load deformation relationships. This is just for upper floor response, and this is for response for base isolation devices. So you can see in the upper floor, the response is almost linear, or linear elastic, but for base isolation, you can see the highly nonlinear characteristics appears in the base isolation system. So we have to predict such nonlinear characteristic to predict upper response. But it's difficult to predict such system without SSM system. But using a SSM system, so such nonlinear amplification characteristics can be modeled using observation records. So even the empirical amplification factors and or the spring mass model can be tuned by using these data. So currently, I'm modeling these amplification from basement to upper floor by a simple empirical relation divided, categorized by small amplification and large amplification input. So this is a result of power spectrum focusing at target site from front side P wave data. This is a basement result. For the introduction, this is a frequency, and this black curves the power spectrum at Oscar P wave. This must be estimated at real time. And this blue solid line is a prediction at illness basement from a spectral ratio between the Oscar to illness basement for empirical estimation by using these data. And the blue dots are observation. So it is a good agreement as a EEW system. And this is a comparison for the top floor. So the solid line is a prediction and dot line is observation. So, and the agreement is good. So by combining an EEW system with SHF system, such a site-specific spectrum focusing system become possible. not only for the basement input motion, but also upper floor response. So you can predict upper floor response in the EW system. So after the earthquake, you can use the SHM system as a usual case. So this is a deformation, estimated deformation, and this is a natural frequency drops, and this is the damping factor. So you can see the this is a system identification by subspace method. So you can see the displacement is just 2 centimeter. It's not so large, and the natural frequency is dropped but recovered after the earthquake. And you can see the damping factor is for the first and second mode is very large. This is probably contribute to reduce the upper response, upper structure's response. So I have to note that such SHM function can be conducted even at distance buildings like Oshika or the other buildings by if the such SHM is in the real-time network. So this is my final slide, and this is SHM with EW framework. So in the normal stage, normal small earthquake stage, this structure health monitoring or real-time EW network system can be used to tune building model or from P to target S ratio by using these data. And at the strong motions occurred, earthquake occurred, spectral focusing using this tuned from P to target ratio with real-time P wave at front side. And after the earthquake, we can conduct as SHM to check the structural safety and if the people can stay in the building at each buildings. So SHM with EW can be used to establish site or building specific spectral forecasting model. And SHM monitors a building state continuously before the earthquake, during earthquake, and after the earthquake, and can be used to improve the accuracy of the structural forecasting and structural response and focusing by EW. This is the end of my presentation, and thank you for listening.
Thank you so much, Professor Ono. That was very interesting. Yeah, I've never seen that kind of framework before. So I didn't receive any Q&A questions in the Q&A box, but I'm just wondering if anybody has any questions that they would like to ask regardless. If not, then I have a question, Professor Ono. So I'm just wondering how kind of widespread is structural health monitoring in Japan? So, I mean, how kind of how widespread could your framework become?
Yes, structural health monitoring become popular after the 2011 Tohoku earthquake. This is because there are a strong shaking in the Tokyo area, especially for なんていうかな、long period component structure like super high tall buildings, and because due to long period ground motions, and people, residents want to know if the buildings is safe or not. So after the 2011 Tohoku earthquake, such a structure health monitoring system has been increased, but probably this is not connected to a real-time network. This is individually installed and connected to a not connected to a network. So if the such SHM system connected to EW system, I think it is very useful to improve the accuracy of for EW for predicting a flow response during the earthquake.
Yeah. Great. So we did get one comment in the chat by Dr. Parole. I don't know if you want to say anything out loud, Dr. Parole, or not. That's fine. But he did mention, Professor Ono, that there might be some papers in the chat that you want to read. Yeah, we can't hear you, Dr. Parole, but there's some papers that he mentioned that you might want to read in the chat, Professor Ono. But thank you very much again. That was very interesting. Okay, so next up we have Dr. Gordon Wu of ORMS. So Dr. Gordon Wu is a catastrophist at ORMS, and he's a world-renowned expert on risk, particularly catastrophe risks. Among his many achievements is 2 books, The Mathematics of Natural Catastrophes and Calculating Catastrophe, which are very well acclaimed. And Gordon has told me that he delivered this particular talk at the USGS in Menlo Park back in October 2019. So we're very, very fortunate to have Gordon here today. And thanks very much, Gordon. The stage is all yours.
Well, thanks very much, Gemma. The background to my talk is as follows. At the end of 2014, I happened to meet Richard Allen, the noted professor at Berkeley, who is one of the world's leading proponents of earthquake early warning. And he was telling me at that time that he was struggling to get the necessary funding for an earthquake early warning system in California. This was at the end of 2014. And when I met with him, I asked him if there had been a study of the cost effectiveness of an earthquake early warning system in saving lives in California. And he told me there had not been. So being a catastrophe risk analyst, I set about in 2015 in doing such an analysis. And this is what I'm going to be describing to you today. Just to give you more background into the whole financial arrangements for earthquake early warning, the state government of California had passed a law stating that there should be an earthquake early warning system in California. However, the law stated that the California taxpayer should not be paying the bill for it. Okay, so the state government of California wanted the federal government essentially to pay for it, or else some private donors. Now, the problem there was that when President Obama was in the White House, he gave some money for the development of an earthquake early warning system, just enough to get it started. And when President Trump took over at the White House, he slashed the budget for this. And here we have the headline of the Los Angeles Times in February of 2018. And I draw your attention to the bottom of this quote from the Los Angeles Times, where the US Department of the Interior, which oversees the US Geological Survey, said in its budget justification that the reduction in the earthquake hazards program was proposed to address higher priorities. Now, one can ask the question, what are higher priorities than saving the lives of Californians? So this is the question I'm addressing in my talk. For those of you who don't know where RMS's head office is, it happens to be in a town called Newark in the Bay Area of San Francisco. And the office is quite close to the Hayward Fault. So this whole question about earthquake early warning is one which matters to the staff members of RMS, whose well-being is very much at stake if there were to be an earthquake on the Hayward Fault. Now, turning the clock back to 1868, there was a major earthquake on the Hayward Fault, a large earthquake, magnitude 6.8 to 7.0. 30 people were killed out of a Bay Area population around 260,000. And on the slide is shown an intensity map for this major earthquake, which was back in 1868. And there was damage to the town of Hayward and some other nearby towns at that time. RMS's core business is doing analysis of loss, primarily for the insurance industry. And back in 2008, RMS produced a report on what the loss consequences would be if the 1868 earthquake were to recur. And this uses a database of properties in the state, which includes information on the age, building style, soil conditions, etc. And this enables the earthquake vulnerability of a property to be assessed. So once one knows what the ground motion footprint is for an event, then the damage at each location within the footprint can be estimated and the overall portfolio loss can be aggregated. Now, the 1868 event is seminal for earthquake early warning in California, because it was way back in 1868 that a physician, not a physicist, a physician, Dr. J.D. Cooper, proposed an earthquake warning system. And this was based on the appreciation that telegraph signals could be sent from the epicenter across the bay to San Francisco much faster than would seismic waves. And so his idea was to have an earthquake bell which would ring out above the city center in San Francisco when shaking was on the way. Now, this was in 1868. And California has had to wait right into the 21st century for this dream of Dr. Cooper's to be realized. Now, when it comes to spending money on earthquake risk mitigation, it is useful to compare alternatives. Now, take the Golden Gate Bridge. This cost $645 million for retrofitting. Now, anyone who lives in Marin County knows that if the San Francisco bridge here at Golden Gate, if this were to be damaged, which would mean the loss of the opportunity for traffic to go across the Golden Gate Bridge, this would be horrendous in terms of those living in Marin County, which is to the north of San Francisco. So this cost for retrofit, $645 million, is money very well spent to keep the bridge open in the event of a large earthquake. And indeed, this money has been earmarked for the retrofit. However, if you take an earthquake early warning system for the west coast of the United States, this would cost $38 million to install and $16.1 million annually to operate. Now, this is the question: is this cost effective? The problem is that the mitigation of casualties is limited by three factors. First, there is a blind zone. So if you're too close to the epicenter, then you won't get any warning. Secondly, the quality of seismic construction in California is generally excellent. So the chance of having serious damage in a building is comparatively low. And thirdly, if you're unlucky enough to be in a building which actually collapses, then an earthquake early warning would not actually be very effective, because if it collapses, you'll be stuck in a building and suffocated or injured or whatever. So these are three factors which mitigate the effectiveness of an earthquake early warning system in California. Now, in order to try to understand what the cost effectiveness is of an earthquake early warning system, one goes through the typical process for any kind of catastrophe risk modeling assessment. Namely, we start off with a stochastic module defining the earthquake. Secondly, we have a hazard module where the ground shaking is assessed for each event. Thirdly, we have a vulnerability module whereby the damage for the ground shaking is evaluated. And finally, we have a financial module which converts the damage into financial loss. Now, this is the typical catastrophe risk modeling process. For the application of interest here, the financial module is effectively replaced by one which attempts to estimate what the human loss consequences are in terms of injuries and deaths. I'll just quickly go through the basic steps. So first of all, we start with the hazard model, which comes from the USGS standard Uniform California Earthquake Rupture Forecast, UCL-3. Then we have ground shaking model, which has been developed largely at Berkeley through the Pacific Earthquake Engineering Research Center. Then we have the seismic vulnerability model, which takes into account the damage distribution of structures subject to earthquake ground motion. So those are the basic ingredients for the kind of risk evaluation that is required for this cost effectiveness study. But before I go on to describing the details of that, I'd like to bring you back to the 1906 Great San Francisco earthquake and fire. I think most people know that there was a substantial amount of earthquake damage, which was exacerbated by a citywide fire, which spread in a fairly uncontrolled manner, which caused a huge amount of damage. Now, with that as a background, I'd like to draw your attention to aspects of fire regulation for new California homes. The California Building Standards Commission approved the State Fire Marshal's Building, Fire, and Residential Code Adoption Packages for the 2010 California Building Standards Codes. And as of January 2011, residential fire sprinklers have been required in all new 1- and 2-family dwellings and townhouses statewide. Now, these are fire sprinklers, not fire alarms. Now, fire alarms are very cheap and easy to install and so on. But to install fire sprinkler systems is a lot more expensive. Typically, it's well known that all offices have fire sprinkler systems, but this is not true at all for ordinary residential homes. So this was the law which came into being in California in 2011. Now, an obvious question about this law is whether it is cost effective or not. Is it worthwhile Californian homeowners spending several $1,000s to install these sprinkler systems because fires are fairly rare? It turns out that there was a major study done by the US Fire Administration in conjunction with FEMA. And this study established that indeed it was cost effective for this regulation to be passed. And this study was based on how much willingness there was to pay to save a life from the fire hazard. Now, this was a study done in 2007. That's when the report was produced. And for the study, they used, back in 2005 dollars, a value for the willingness to pay to save a Californian life of $8 million. That's in 2005 money. And if we convert that to 2021 dollars, this would amount to about $11 million. Okay, so it's quite a substantial amount of money that society is willing to pay to save a life against fire hazard. Now, moving on to earthquake risk in the state of California. In 2014, which is one of the most recent damaging earthquakes in the state, an earthquake occurred in South Napa. And this is a slide just showing some of the damage from it. One of the clear lessons from this earthquake is that it's better to stay indoors rather than to try to run outside because of the risk of falling masonry. So this automobile was badly damaged from falling bricks. The standard instruction in the event of an earthquake is duck, cover, and hold. You duck under a table or desk, cover your head and hold on to a table leg for protection. So duck, cover, and hold. Now, if you ask the question, what is the value of having a few seconds of earthquake early warning? Well, one answer is this, that if you imagine a typical apartment layout, such as shown on this slide, as I said, that what you need to do in the event of ground shaking is duck, cover, and hold. But you may not necessarily be in a place where there is a suitable table to duck, cover, and hold. Okay, so if you imagine an apartment with a layout such as is shown, then with 1 second, you could just literally get on your knees and find a table within arm's length or whatever. If you had 8 seconds, you should be able to find a table in the same room. If you had 15 seconds of warning, you could find a safe place in a room next door, an adjacent room. And if you're lucky enough to have 22 seconds, you could find a safe place somewhere in your apartment, perhaps a few rooms away. Now, with that in mind, this is just an illustration here of a dining room in one house in Northern California. And you can see that this would be a very suitable table to duck, cover, and hold under if you happen to be in that room at the time. If you weren't, then if you had a few seconds, then hopefully you could find your way to this dining room to duck under it. And you can see from the chandeliers here that if you were under the table, then you would be protected against the chandeliers falling or parts of the ceiling falling down. Now, Richard Allen and co-workers produced diagrams which charted how much warning time you would have as against the distance from the earthquake epicenter. So for distances of 16, 25, 50, 75, and 100 kilometers from the earthquake epicenter, the amount of warning time given is shown as on this chart. This is published in Seismological Research Letters Now, turning back to the apartment layout, one could figure out that if you only had 1 second of time, then DCH delta is duct cover and hold delta is what proportion of occupants might be expected to be able to find a place to duck under. And maybe that's a quarter if you've only got 1 second. If you had 8 seconds, then maybe half the people could find a suitable place in the same room. If you had 15 seconds, maybe 3/4 could find a suitable place. And if you had as much as 22 seconds, then maybe most, if not all people could find a suitable table to duck under if you had that extra amount of time. Now, to put this in a quantitative framework, for each building of construction class Y, which could be wood, unreinforced masonry, reinforced concrete steel frame, etc. For a given damage ratio, we can denote the proportion of those occupants who do not find a suitable place and who suffer injury severity level I. We denote this as F0 YLI, and the proportion of those occupants who do manage to find a safe place who suffer an injury severity level I, we denote that as FS YLI. Y is the construction class, I is the injury severity level. Then in the whole population, we have a mixture of those who do find a safe place and those who do not find a safe place. And so we can calculate the overall proportion of occupants who suffer an injury severity level at a given percentage distance. And this is shown at the bottom equation. And if we just introduce a parameter lambda, which is essentially what the reduction factor is in the proportion who would suffer injury, then as we change the value of lambda, we end up with a table like this. So if lambda is 1, then essentially there's no benefit. But if lambda is 0, then essentially we're full benefit. So for a wide range of different types of construction, different epicenters, and these parameter values lambda, we can come up with these mitigation factors, which can enable us to help assess what the reduction in injury and fatality is for each earthquake which happens. And in order to do the seismic hazard part of the calculation, we use the fault sources as designated by the Working Group on California Earthquake Probabilities. This is published by Nedfield et al. In BSSA. Also, from the same publication of BSSA, we have the 30-year exceedance probability ranges, average to maximum, and these are done for all the principal California faults, and also for the principal scenarios, magnitude 7, magnitude 7.5, and magnitude 7.9. And what myself and my RMS colleagues have done is to run a California earthquake loss model to figure out what the expected number of lives saved indoors is for the different scenarios. Okay, so we have the Rogers-Hayward Creek event, magnitude 7. That was the event which I notified you about at the very start of this presentation. The expected number of lives saved is 80. For the South San Andreas fault, it's 100, and so on. A further aspect of this analysis which needs to be mentioned is the fact that earthquake early warning can save fire loss. So what's been done here is to consider a particular scenario, which is a magnitude 7.8 Southern California shakeout scenario, where as many as 1,600 ignitions have been simulated. So this would be a very disastrous event in terms of fire loss, with the burnt area estimated to be $40 billion. So the average fire loss per ignition is $25 million. Now, this scenario has about a 10% chance of occurrence in 30 years. So the expected saving in fire loss from this single California disaster scenario might be estimated at, say, around $40 million. So that seems like a reasonable figure for how much money you could save if you could prevent 1% of these ignitions from happening through an earthquake early warning ignition control system. Now, having said that, we can move on to the key numbers which come out of this analysis, which are as follows. That the earthquake early warning system is going to require $16 million of operational costs for 30 years, which is about $500 million. Now, if you have a willingness to pay of $11 million to save a life, then if you could save just 50 lives in that period of 30 years, say a couple of lives a year on that kind of order, then on these grounds alone, an earthquake early warning system would be fully warranted. So when President Trump was arguing about the priorities of this, then this analysis shows that the implementation of this earthquake early warning system will be justified even if you only saved 2 Californian lives a year as a result of this. Now, the fact of the matter is that because of the high standard of earthquake construction in California, there have been less than 200 earthquake deaths in California over the past 60 years. So I mentioned the South Napa earthquake of 2014. And in fact, there was just one fatality from this earthquake. Regrettably, one lady died of a brain hemorrhage following TV falling on her head, which is tragic, obviously, but there was just one fatality from that earthquake. And most recently, for the Ridgecrest earthquakes in 2019, the main shock there was magnitude 7.1, and there was only one fatality from this, and that was not even in the state of California, that was actually in the state of Nevada. So there again, there was no local fatality. And what this shows is that with the high standard of earthquake engineering in the state of California, saving lives is something which occurs occasionally. It's not like you'll save many lives from an earthquake early warning system. So apart from saving lives, these are obvious other benefits from an earthquake early warning system, which are just common sense, really, that we're going to have fewer industrial accidents, more resilient economic recovery, less post-traumatic stress disorder, greater peace of mind amongst the local population, as well as visitors. And last, I'd just like to draw attention to the fact that turning the clock back to 2010, I was actually in Santa Monica for the Baja California earthquake on Easter of that year, and I was actually on the pier when there was a slight swaying of the pier in response to this distant earthquake, and even at that time, one thought, well, it would be great if there were an earthquake early warning system so one knew about this kind of event as soon as it happened. And you see the Ferris wheel in the background of this picture. In the past, people have tumbled out of Ferris wheels when there have been accidents of various types. So in the case of earthquake early warning, then it is possible that if they were shaking at a time when people were on this Ferris wheel, then there could be some injuries resulting from that. So so the whole concept of an earthquake early warning system is clearly something which is of societal value beyond just the saving of lives. And I'm happy to say that this is a presentation with a good ending, because literally just a few weeks ago, there was an announcement that the entire US West Coast now has access to shake alert earthquake early warning. This was a statement issued by the USGS literally just a couple of weeks ago. So I'm very pleased to give this presentation with this happy news to end on. So with that, I'll end this talk, Gemma. Thank you.
Thanks a lot, Gordon. Very, very interesting, and it's great that it ended so well. So yeah, we've got a few questions in the chat. So what I might do is I'll read them out, and if the person who asked the question wants to also chime in, please do. So Julia says, I'm wondering why everyone couldn't find a safe place within 8 seconds. After all, drop, cover, hold, as it is taught, doesn't require you to find something to get under. It also means that you can drop, cover, hold on the spot.
No, that's a very good question. But in fact, the point I'm making is that drop, cover, and hold could be more efficient if people manage to crawl into a safer place than where they just happen to be at the time when the earthquake early warning is sounded. Like, for example, supposing you happen to be in the bathroom at the time, shall we say, okay, and supposing that there's just no place to duck, cover, and hold under, then if the ceiling came down, even if you covered your head with your hands, for example, you could still be in trouble. So the point I'm making is that if you just had those few extra seconds, you could manage to crawl under a more a safe place than where you just happen to be at a given time.
Okay, so we have, so I just realized as well, actually, I think I need to allow anybody to talk. So let me know if you want to talk, but we have some comments from Keith Adams. So his first comment was disability and mobility issues. And I think he was referring to the risk reduction effect that would occur in that case.
Yes, well, that's a very good point. I think that those people, obviously, this whole idea of trying to get under a table is basically to do it as best as one can. But the problem with people who have mobility issues is that clearly if they're not under protection like a table or whatever, and there is some significant damage, say to the ceiling or whatever, then they would be in serious trouble. So yes, that is another factor. I should say that these questions all relate to this. Again, the core issue, which is how much benefit is there if you just have a few seconds of warning? I mean, that is the key question, right? And and so what I've tried to do is actually and what in fact does require this kind of modeling is in fact a systematic type of analysis, which can really help identify exactly where and what are the key savings which can be made.
Yeah. Keith also, so I'll just go to the next one that Keith mentioned, but he said that the California economy is one of the largest in the world, more than capable of funding an earthquake early warning system without federal help. And Keith, I allowed you to talk in case you want to also chime in.
Yeah, sorry, I was just making the point really that I think the issue with Donald Trump was to do with the states taking responsibility for their own emergency.
Yes, well, that's a great question. In fact, I know exactly where you're coming from. In fact, the reason why I got into this in the first place was very much along the lines of RMS having a public policy role of trying to reach out to some of the corporations in Silicon Valley to try to encourage them to help contribute to the cost of earthquake early warning. And the point I made was that it doesn't matter if you're working in extremely well-designed building, say in Cupertino for Apple, okay, because one evening you may find your way down to Chinatown in San Francisco and having dinner in a building which is highly vulnerable. Okay, so in fact, at the time when I got involved in this, part of the idea was that RMS could help reach out to corporations in California to try to encourage them to contribute some money to the cost of this earthquake early warning system. So that was kind of the basic idea which was in my mind when I embarked on this work.
Yeah, absolutely.
I'm muted. We have a question from Simona Colombelli. Does the cost effectiveness analysis take into account the occurrence of faults and missed alarms? Perhaps these should be included to evaluate the effectiveness of the system. And Simona, I also allowed you to talk in case you want to mention anything else.
No, I mean, there's no specific allowance for false alarms. And the point about earthquake early warning in terms of false alarms is that I always make the analogy with fire alarms, because in my old office building, which is in the City of London, we had a false fire alarm probably every few months or so. Okay, and when the fire alarm went off, everyone evacuated the building for usually about 15, maybe half an hour, 15 minutes, half an hour. Okay, but no one ever complained about this. Okay, and this is the point I like to make, which is that even though the chance of a fire was very small, nobody complained about these false alarms. A, because they were fairly brief, and because each fire alarm itself is a form of fire training. Okay, so that's why I must say this is a key issue of safety policy, which does need to be emphasized, which is that these occasional false alarms, like for this, I think it's a price which should be paid by, the public should be willing to pay for preparedness for a real event.
But I suppose, could you argue then, you know, in that 15 or half an hour that you were outside your office is 15 minutes or half an hour of lost business?
Yeah, but the point I'm making is that everyone knows, everyone who worked in an office knew that if they're out of the office for 15 minutes or whatever, they would make it up somehow over the week or whatever. Okay, it's just everyone expected that. Okay, yeah. So it's part of working. But in fact, like in the RMS office, literally, it was completely a red line not to evacuate when you're told to. It was essentially it was absolutely disallowed to ignore a warning to leave the building. Even if you knew it was a false alarm, like if you knew that someone had burnt the toast, so you knew that it was a false alarm. Okay? Yeah. It was absolutely not allowed to ignore it, and which is exactly the right policy, I should say. Okay, but I think that there's a lot which can be learned by sharing experiences across perils. Okay, like with false alarms for fire and so on. But I think within the context of an earthquake false alarm, we're talking here about literally like a few minutes or something. It's not like an operational earthquake forecast which would last for hours. I mean, this would be just obviously a matter of minutes. And so I personally would take the view that these kind of false alarms is the kind of price that society should be prepared to pay in order to be better protected.
Mm-hmm. And Gerald asks, can you please repeat your approach to estimate the number of people's lives that can be saved with the early warning system under different scenarios?
Yes, I mean, but I did outline it. I should say that I do have a publication which has more information on this. But essentially, what we want to do is to estimate those people who would be in a situation where they can't, they don't have a table to duck under or whatever, and so for given levels of vulnerability, then essentially there's a connection between those who find themselves in a building which is damaged but not destroyed. If it's destroyed, then of course, if somebody does die, then their lives wouldn't have been saved anyway. But the key component of the analysis is that for buildings which do suffer damage, but where people manage to get under, say, a table to duck under, whereas without the warning, they would be out and potentially might be crushed by falling plaster or ceilings or whatever.
Great, and Anawat just mentioned that there's a paper in, I think it's the International Journal of Disaster Risk Reduction, about the willingness of people to pay for earthquake early warning in California. So he's just shared that paper in the chat in case anybody's interested. Great, thanks a lot, Gordon.
Okay,
that was very interesting as always.
Okay.
So next up is myself and Gianluca from UCL, and we're going to talk about some technical and social organizational components of earthquake early warning. So I'll just share my screen. Okay.
Yeah, looks good. We can see your screen.
Okay, thank you. All right. Okay, so I'm going to talk firstly about advancements for risk-informed earthquake early warning from a technical perspective. And I did this work with Carmina Galasso at UCL, and we did this under the TURNkey Research Consortium, which is a €8 million 3-year research project funded by the European Union. And it involves about 21 partners across 10 different countries. And the purpose of the research project is to promote urban resilience through the development of innovative technologies. And one of these technologies is earthquake early warning. So the first part of my presentation will focus on calculating the feasibility of earthquake early warning across Europe. So if we were to install an earthquake early warning system across Europe, really how beneficial would that system be? Many of the speakers before me have discussed in detail exactly what goes into an earthquake early warning system, so I'm not going to discuss that here. But I am going to focus on a regional version of earthquake early warning for the first part of this presentation. And what this means is the sensors that are used to detect and estimate the characteristics of incoming earthquakes are spread throughout a region of high seismic hazard in this case. And we're particularly assuming in this case that the seismic sensors that are already installed across Europe would be used in a future earthquake early warning system if it were to be installed in the continent. So what we need to understand in this case is where earthquakes occur in Europe, where seismic stations are located in relation to where earthquakes occur, and also where the end users of the system lie in relation to the seismic sensors and the earthquake sources. So we're particularly interested in the target sites that are shown on the map on the right-hand side of the slide. And what we do is we take all of the area sources of high seismic hazard that surround these target sites. We try to understand the speed at which seismic waves would emanate from these seismic sources. And we also take the seismic sensor locations for stations that are located close to the sources. We combine all this information, and what we do is we produce a lead time map. Now, what this lead time map tells us is the amount of time that these target sites have between when an earthquake would be estimated and detected by the sensors and the models that underlie the earthquake early warning system, and when the strong shaking would actually hit the target sites. So lead time, in a way, is an indicator of the potential beneficial effect of earthquake early warning across the continent. So this is just one lead time map that we could get if we considered one area source for each target site. But in reality, each target site is affected by a number of different area sources. So what we can do is we can do this lead time calculation for each of the area sources that affect each target site in an iterative process to come up with a lead time distribution for each target site. And then from this distribution, we can construct a number of different maps, such as a minimum lead time map, a median lead time map, and a maximum lead time map. So minimum is obviously the worst case scenario, and maximum lead time would be the best case scenario. And what we see in the best case scenario is that a lot of the target sites have at least some positive lead time or warning time. And this depends on some assumptions that we've made in the underlying calculations, but this is a potentially positive indicator for earthquake early warning across Europe. Now we can go one step further than this and not just consider the amount of warning time that an earthquake early warning system would give us, but also consider where the population lives in relation to the amount of warning time that's available and the type of shaking that the population might be exposed to in future earthquakes from the area sources we're considering. And this gives us a deeper insight into the potential beneficial effects of earthquake early warning across Europe. So we can combine all this information together to come up with plots like this, which show us the population on the y-axis as a function of the amount of lead time they have and shaking that they might experience in future earthquakes. And what we see is that a notable proportion of the population has either positive, median, or maximum lead time for relatively strong shaking. And again, this is a positive indicator for the potential beneficial effect of earthquake early warning in Europe. Now, we can go kind of one step further and more formally measure the feasibility potential of earthquake early warning using what is known as a relative feasibility index. And this is a metric that we proposed ourselves. And what it does is it combines information on the amount of population that's exposed at a particular site, the amount of shaking that they might experience in future earthquakes, and the amount of warning time that they might have in future earthquakes into one particular index. And what this index does is it measures the feasibility of earthquake early warning of a particular target site relative to all other target sites. So the maximum value of this index would be 1, and that would occur for a target site that had the maximum amount of population around it relative to all other target sites, the maximum amount of median lead time, and the maximum amount of seismic intensity from future earthquakes. And we've also introduced weightings in this index, and this is to accommodate different stakeholder preferences. So you could imagine that maybe one stakeholder is more interested in an earthquake early warning system that provides good warning time. Another stakeholder might only be interested in providing earthquake early warning if there's a sufficient population around the system. But in this case, we're going to use the equally weighted approach, and we can get a plot like this, which shows the relative feasibility index for regions that have a positive median lead time across Europe. And we can see that the most feasible sites for earthquake early warning are located in either Italy, Turkey, or Greece. So in conclusion, for this first step in our calculation, we see that a large proportion of the target sites have some positive lead time in a best case scenario, and therefore we can conclude that earthquake early warning could be beneficial within a holistic suite of earthquake risk reduction tools, which is something that Gordon mentioned. Of course, earthquake early warning can't solve all our problems, but it can be used as a helpful supplemental tool. And finally, we saw that the most feasible sites for earthquake early warning in Europe would be in Italy, Turkey, and Greece. And the results of this study will hopefully be out soon, and you can see some more calculations we did there in the future. Now on to the next part of the presentation, which focuses on decision-making for earthquake early warning and the decision module in particular, where basically the estimated characteristics of the incoming earthquake are used to make a decision on whether or not an alert should be issued so that people can take the protective measures. Now, in this case, there's two main limitations associated with decision modules in operational systems across the world. One is that the decision is normally made on seismological characteristics of the incoming earthquake, as Dr. Hoshiba told us, rather than kind of a more rigorous engineering-based consequence predictions. And the second limitation is that the decision fails to account for diverse stakeholder requirements. So we address these two limitations in a new method we developed, which integrates earthquake engineering seismic performance assessment procedures with multi-criteria decision-making tools. Now, in this case, what I mean by a seismic performance assessment procedure is similar to the catastrophe risk framework that Gordon showed us, where basically we could take an example of the FEMA P58 methodology for individual buildings, where the earthquake is translated into effects on the built environment in the form of particular loss metrics like casualties, downtime, and economic loss. And then these outputs can be merged with multi-criteria decision-making, which involves the following steps on the part of a stakeholder. They need to tell us the criteria on which they want to base their decision on whether or not to issue an alert. They need to give us the importance of each of those criteria for them. So are they more interested in one criterion over another? And finally, they need to provide values for some of these criteria in some cases. And the criteria are closely linked to the outputs of the seismic performance assessment procedure. So that's how the two components of this methodology connect. And we'll see this more clearly in the following slides. But let's look for a second at how multi-criteria decision-making for triggering earthquake early warning alerts in a school might look like. So in this case, the stakeholder might have identified the following criteria. They might want to maximize safety, maximize productivity, and maximize public satisfaction. And what we do is we translate these criteria into quantitative indicators. So maximizing safety could be quantified as minimizing casualties, maximizing productivity could be quantified as minimizing disruption. And it's these indicators that are actually outputs of the seismic performance assessment procedure in the first component of the methodology. And the values of the indicators for a given incoming earthquake and a given mitigation action and the importance of the indicators to the stakeholder are what determine whether or not an alert will be issued for an incoming event. So let's go through this in a bit more detail. Firstly, what we do is we summarize each of the identified criteria and each of the possible actions in the form of what we call a consequence matrix, where each column corresponds to a particular criteria and each row corresponds to a particular action, and then each entry of the matrix gives us the value of the particular criterion for the given action. Now, some of this information in the matrix comes directly from the stakeholder, and that's related to consequences associated with false alarms, which we discussed in a little bit of detail previously. The second source of information is a combination of both stakeholder input and our performance-based earthquake engineering analysis. And this is information related to the actual mitigating effect of a mitigating action. So how much can an action actually reduce the losses of an incoming earthquake? And then some of the information comes directly from our performance-based earthquake engineering seismic assessment procedures. And this is information related to when we don't take an action. So if we don't take an action, we can think about it as kind of a conventional seismic risk analysis that we're doing. The only difference here is that we have some uncertainty on the characteristics of the incoming earthquake, like its magnitude and its ground shaking, that we need to consider when we're doing our seismic risk analysis. Once we have the consequence matrix, we can translate that into a decision matrix, which has the same entries as the consequence matrix, except they're normalized and they're also weighted by the stakeholder preferences towards the different criteria. And the final step is to take the particular mitigation action that minimizes the collective values across the decision matrix, because in this case, all of the criteria are losses. Now, we saw how the consequence matrix gets translated into a decision matrix to determine the optimal action. What goes into the consequence matrix is the estimates of the incoming earthquake from the earthquake early warning system, as well as outputs of the seismic performance assessment procedures. And the missing piece of the puzzle then is the stakeholder input, which goes into both the consequence matrix and the decision matrix in the form of stakeholder preferences towards different types of criteria or losses. So let's look at a quick example of this methodology for a school located in Palo Alto, California. So this is a hypothetical school. And in this case, we're going to assume the criteria are the same as what we discussed previously, and that we only have two possible actions. Either we trigger the alarm or we don't trigger the alarm in this case. Now, the question we're going to answer in this particular example is, what is the optimal action as a function of ground shaking? So in this case, we're going to assume that the earthquake early warning system is providing us with ground shaking estimates. And we get a plot that looks like this, which shows us the optimal decision as a function of the incoming ground shaking estimates, expressed as spectral acceleration at the fundamental period. And we have optimal decisions as a function of different stakeholder preferences towards different criteria. And we can answer questions like, how often is the alarm triggered? So we see that if we look at the plot, the optimal action is to trigger the alarm about once every 10 years if casualties are weighted the highest. But if downtime is weighted more heavily by the stakeholder, we would only maybe trigger the alarm at once every 20 years. So really what this plot is telling us is that stakeholder preferences towards different types of risk are a really important ingredient in determining whether or not a particular mitigation action should be triggered for an earthquake early warning system. So in conclusion, we developed this methodology that merges seismic performance assessment procedures with multi-criteria decision-making tools. it was demonstrated for a hypothetical school, which showed us that stakeholder preferences towards different types of risk, as well as of course, the strength of the incoming ground shaking are important for determining the optimal action. And the last thing to take away from this particular study is that this plot I showed here can be computed ahead of time. It doesn't need to be computed in real time. All we need to do in real time is determine the ground shaking estimate, and then we can consult this plot, taking into consideration stakeholder preferences for very efficient real-time decision making. Thank you for listening. And now I'm going to quickly move to Gianluca. Gianluca, are you there?
Yeah, but you need to habilitate my video.
Okay. I don't think it says that your camera is off and that you have the ability to turn on your own camera.
No.
Okay.
I mean, I say it's literally unable to start video. You can start your video because the host has stopped it.
Okay.
You can send this screen share if you want.
Okay. Maybe if you just go ahead with your presentation. I'm sorry, and I'll try and figure it out while you're doing it.
Okay, I can do that, but please have a check on this. Can you see less my screen sharing?
We can see your PowerPoint, but not the proper.
Okay. So I will just use my PowerPoint.
Okay.
So can you see now?
Yeah, perfect.
Perfect. So welcome everybody. My session will speak shortly of what engineers do not tell you normally. So the dark side of earthquake early warnings and the social dimension, organizational dimension to it. So first of all, welcome to all. If you don't know me, I'm Gianluca Pescaroli. I'm lecturer in business continuity and organizational resilience and director of the Master in Risk, Disaster and Resilience at the Institute for Risk and Disaster Reduction. So I founded the research group on cascading disaster specs in 2016, and I tend to do quite applied research, including a contribution to UN World into Action guidelines for national risk assessment. The last published report by the European Commission, the flagship report Science for DRM 2020. The hazard classification and definition review. And most of all, as you can see from my background, I have also the best coffee at UCL when we are on campus. So whatever you need, drop me in the office when we'll be back and have a chat. So my plan today, I have little time, so I'll go directly to the point. I will introduce the socio-organizational component on earthquake early warnings. Then I will explain you shortly the application for business continuity and emergency management, and we'll have most of the time left for question and answers. So the social organizational component of early warning systems. So back in our research in 2018, this is the published paper I had with Professor David Alexander on the difference between compound, interacting and interconnecting and cascading risk. So complex scenarios. We demonstrated already that whoever and whatever we see these problems, there are different components at the disciplinary level that can match together. And this including on the physical side, modeling, forecasting, network analysis, and resilience assessment more on the vulnerability side. But at the end of the day, earthquake early warnings is one of those where the component that Gemma was mentioning to what I'm doing merges better. And the reason is that there is the technical component, but the way we translate the technical component in how we do things, we need to understand the context and we need to understand the practices of how things are done. So technology, structural aspects, physical aspects are essential. However, they depend on the context where they are developed and they are socially determined. So look the picture you see now. We have a pair of red shoes. We walk in them, and we walk in them every day. We can have nice things, but depending on the context where we are and what has been done around us and around our policies, our situation, our vulnerabilities, the red shoes can become really different. So they can become also an aspect that if we don't understand the situation, well, it's a critical point, right? Like you see in the picture now. So the technical aspect is essential to walk, but the way we understand where are we walking and how makes the completely different in the use of technology and in its effective use, most of all. So in a paper that we just published, we defined the four spheres. Sorry. One is operational, so tactical elements and tools like social media, sirens, information on lead times. Then political and governance, so political and legislative issues, laws, accountability and management, societal and behavioral, my God. Technology, remember, technology can go wrong. The way you use this thing that technology goes wrong and the way you understand which are your vulnerabilities make the difference on how you manage it. So social and behavioral, people's knowledge and perception, like what I'm doing now with the slide that go mad. The example, local culture, trust, experiences, vulnerabilities, and organizational dimension, like procedures on early warnings, public utilities, and activation of business continuity planning. So we applied these four spheres in 4 case studies. One, clearly, as you may have understand already, this is Italy, and this is in particular southern Italy in Campania and in Lucania, where there is the early warnings that Gemma was mentioning. Then California and the East Coast, Mexico, and Japan. So we compared those case studies and the challenges in implementing earthquake early warnings in the operational sphere. One second. Operational sphere, I put it like that, otherwise it's going completely mad. And we define that on the operational thing, so technical, there is still an open discussion about what the information, the use of information, and how earthquake early warning alerts should be transmitted. In the political and societal sphere, we have seen that official bodies such as civil protection need to improve the training for response at the community level and at the organizational level. And accountability and liability procedures should be addressed within, together, the same implementation of the technical aspects. Then we have societal and behavioral sphere. In most of the case studies we see with this review that alerts were found useful. False alarms were thoroughly rated by the population and seen in some cases as drills opportunity, like in Japan. But users would prefer to know the available warning time and expected level of shaking. And most of all, they need to be sure what to do when they receive the alert. So in some cases, like in Japan, this is a bit better, clearly. In other areas, like for example, Mexico or Italy, this is still early level. And then we have the organizational sphere. So schools, hospital, transport system can highly benefit from earthquake early warning system. And again, though, the technical component need linkages with the internal procedures and with how first responders and or official bodies manages it. So to give you an idea shortly then, think about how this is applied in business continuity and emergency management, and it looks like this. You would benefit in this particular situation on the warnings and knowing how to do, what to do. In terms of gaps, so how we measure it, even this kind of situation, how can we integrate the different aspects? So you have the technical alert, so angry cat coming. But the way you're gonna prepare and you're gonna manage this thing that goes down can vary about how you are prepared in that situation, what is the gap? So here, the desirable or undesirable state, the capacity level, and the resilience level of your organization or the context in which you're operating. So we developed within a project we had active, the small scale you can find online on the Journal of Disaster Risk Science, that you can apply, for example, for capacity assessment with questionnaires or semi-structured interviews. So you can benchmark to that to understand where are the gaps and where instead you have capacity or less capacity. And overall, what are your resilience level? This can be applied in different way again, depending on your case studies. All the elements we have seen before, all the spheres that society, where society interacts, where are we walking our shoes, can be measured on the social component, depending on which procedure are active, how we do training, how we do communicate at the organizational level, so within a single organization. So you can use, for example, public utilities that in many countries, such as Japan, are supposed to have some planning in place for earthquake warnings. And they have to activate procedures, because the way these procedures and the way the technical element is integrated in how things can be done can make the difference in the reaction time, for example, in activating or not the critical function, put them as safe, like a train that is stopped. But then even in the case of a train that is stopped, are there the legal requirements and the consequences of an act considered in the assessment? And to what extent? The maturity level of this process can be different. Even in the same organization, in the same different aspects, in the same procedure, they can be different aspects that are different level. And the way we can use the expertise of social science is exactly that. Complementary to the technical component, we can understand the other aspects that we are dealing with and to what extent they merge and they are complementary to the technical component. So what happens when the alarm starts? Are everything in place to code it in a different action? There is a lot of work to do in this sector, and we can collaborate on it together. So my time, I think, is already over. Please do get in touch via LinkedIn, ResearchGate, and even I'm a coffee person, I'm always happy with colleagues overseas to take a tea, but it's better that you do it because I'm really bad. So happy to have any discussion. I had little time, but I hope I gave you an idea of how can we work together and how the different aspects again can be complementary. We are talking in generally just about risk perception. This is different. This is capability and capacity assessment and gap assessment. So I would say that if I'm right, I'm exactly over. So Gemma, please, and I'm happy to take any questions and take back any slides that I mentioned.
Thanks a lot, Gianluca. Thanks, that was very good, very interesting. I don't know if there's any questions in the chat. It doesn't look like it to me. Okay, there's no questions in the box either. Okay, everyone's shy. Okay, let's. I mean, we're gone over anyway. So if there's no questions, we can stop here. And just a reminder that we have another session tomorrow from 8 to 10 British summertime, and then Japanese time 4 to 6 on tsunami early warning in particular. So I just want to say thanks very much for attending today. I hope you got some benefit out of it. And yeah, looking forward to seeing you tomorrow.
Right. If you have any question afterwards about what I was saying, please do get in touch via LinkedIn or ResearchGate, okay? Stay safe.
Thanks. I just want to say for the panelists, I will start the WhatsApp, or sorry, not the WhatsApp, the Zoom meeting in a few minutes, so we can have a further discussion. Yeah, thanks.